So in the last class, we looked at this PowerPoint. We started talking about fundamentals of logic. We mentioned the binary concept, the fact that you can think of certain processes or events as being in one state or another. A light can be off or on, a switch can be open or closed, a motor can be running or not running. Anything that lends itself to being in one state or another, you can consider that as being a candidate for the binary concept, which makes it a good candidate to be controlled by a PLC. But the important thing we talked about was this idea of a gate. A gate is going to represent a device that does a particular logic function. And you know by now there's three basic logic functions. There's the AND logic, there's the OR logic, and NOT logic. And then there's other logic functions that are derived from the basic logic function that we mentioned. And so the gate actually performs certain functions. It'll perform AND, OR, NOT logic. And then there are actually gates that perform the derived logic functions that we talked about. So what you see on the screen right now, these are not the gate symbols, but it just shows a kind of a general way of representing gates. We gave a definition of logic, and then we got into the gate representation for the basic logic functions, AND, OR, and NOT. And so what I asked you to do was remember a couple things about each of the logic functions. You want to know the gate symbol. You want to know the truth table. So here on the slide you're looking at now, this is the gate symbol. This is a two-input AND gate. Remember we said that the gates have to have at least two inputs. They can have more. There's no limit to, in theory, there's no limit to how many inputs a gate can have, but it has to have at least two. The only exception is the inverter, which we'll talk about here in a second. That's the only gate that has a single input. Each input on a gate represents a switch that you would have or relay contact that you would have if you were doing a hardwired relay logic. If you were using an AND circuit with switches, then this input would represent two switches in series. The other thing I asked you to remember was the truth table. And this basically is the definition for each of the logic functions. Here, of course, for AND is true only when both switches are closed. So therefore, using the truth table and logic gate representation, AND is only true when there's a 1 on both inputs. For all other cases, AND is false. And if you want to think of it, first week in class we showed an AND circuit wired with switches, basically just two switches in series. And I asked you to make sure you understand the functionality of AND based on switches. But then we abstract from that. We actually use gates to perform AND functions or AND logic. So I asked you to remember the symbol, the truth table, and then there's one more thing we'll get to in a second, the Boolean expression. Boolean is a mathematical way of representing logic gates, logic functions. And so this was the AND, and then we introduced the OR symbol. And remember I said that should be flipped the other way. Typically in electronics, when we draw a device, we show inputs on the left and outputs on the right. So the A and the B should actually be on the left, and the Y should be on the right. But this, of course, is the symbol for OR. This is an OR gate. And you see the truth table for the OR gate. OR is true when either input is true or when they're both true. And then here is the switch representation for OR logic. That the gate I just showed you represents this circuit right here. A two-input OR represents two switches in parallel. And you can see here, if I want to light up the light bulb, all I got to do is close either switch A or B. Either one would provide a path for current to light the light bulb, or if they both are closed, the light bulb will light. Matter of fact, the only time this light in this circuit will not light is if both switches were open. So you can see an OR from the truth table. OR is true, the output is true, anytime there is a true on any input or anytime either switch is closed. So there is the OR. And then this one here is the only one that can have a single input, the NOT. This NOT gate is also called an inverter because it inverts or flips the bits. So we introduce that. And notice I have this variable here, input A. And when that A flows through this chip, it hits this bubble right here, the state of A, the logic state of A flips. And the way you show that flipping of the logic state is by putting a bar over it like that. Now, in some books, they actually, instead of using that bar, they'll have a little prime. Sometimes I'll do that. You'll see a little prime right here. So either this notation or this, it's the same thing. This is called A not or not A, and this is also called A not or not A. So I can use that bar, I can use that little prime symbol right there. I tend to use both of them. Sometimes it's convenient to use the bar, other times it's convenient to use the prime symbol. The not function is pretty simple. It just takes whatever A is and flips it to the opposite state. So if A is a 0, when it hits that state indicator, flowing through the gate, it changes it to a 1. If A is already a 1, it'll change it to a 0. It inverts or flips the bit. And the way to think about that is using a normally closed push button and thinking of the act of not pushing the button as a 0 and the actual physical act of pressing a button as a 1. If the button is not pressed in this circuit, the light is on. If the button is pressed, it's off. And so basically there's a bit inversion, and you represent it using the normally closed push button and the circuit you see before you. So those were the basic gates that we talked about. Well, what we can do is we take those basic gates and we can put them together in different ways to get what we call derived logic functions. And one of those would be this one. This one is the combination of an AND gate and an inverter. And notice, instead of drawing the actual inverter, we just draw the state indicator from the inverter, and we connect that state indicator to the AND gate. And so I have an AND gate that's being knotted by the inverter. So the shorthand way of drawing that is just drawing the state indicator. So that's why in the last class I said when I think about the inverter, I think about a 1 or a 0 actually flowing through the chip. And when it hits that state indicator, it switches to the opposite bit. And if you think about it that way, then whatever flows through this AND gate, when it hits this state indicator, it's gonna change state. And so here what will happen is this A and the B, we don't know the values of A and B right now, but they'll go through and then they'll change. So if you remember the truth table for the AND gate, AND had a 1 here in this row. Both switches had to be closed in order to get an output. And for all other rows, there was 0. Well, if I knot that, if I knot the output of an AND, then I get this. And this is the output of the NAND gate. So a NAND gate is a combination of an AND gate and an inverter. And this is NAND logic that you see here for the output Y. So that is a derived gate. Another derived gate is the NOR gate. And again, please excuse my diagram. The A and B should be on the left. The Y should be on the right. But here you have an OR gate whose output is knotted. And so if you remember the truth table for OR, these were all 1s because either switch had to be closed to get an output, or both switches are closed to get an output. The only time you get a false for an OR is when both switches are open. And so here, if we invert that, then we get what you see here for the output. This is the output of the NOR gate. So we have an AND gate and we have a OR gate. If I knot the output of an AND gate, I have a NAND or not AND. If I knot the output of an OR gate, I have a not or NOR. I just invert those outputs in the truth table, and then I have the truth table for the NAND and the truth table for the NOR. And then there was this one. And I told you to mark this one. This one's really important. This is called an exclusive OR, an XOR. And we use this for a particular thing that we do with PLCs. I'll come back to it later in a few weeks, but put a mark by this. Make sure you study this gate and you study the truth table. The exclusive OR, we need the exclusive OR because it's a different kind of OR. Sometimes when we say OR, somebody had a good example of this in the last class. I forgot exactly what they said, but sometimes when you say OR, you mean either condition or both conditions. And sometimes you say OR, you mean either one or the other, but not both. An example I gave in the last class about one or the other, not both, is that if you go to dinner and you get a menu, and on the menu it says you can have an entree and you can have soup or salad, that means you can have either soup or salad, but not both. That's a case where if you were actually programming that meaning of OR, then you would use the exclusive OR instead of the regular, and I'm doing air quotes, you can't see me, the regular OR. So this one is pretty cool here. You'll see this a lot. So again, you want to know the symbol for the exclusive OR. It's just an OR gate with this little funny looking line on the inputs. And then the truth table is the same as the OR, except for it excludes the condition where both inputs are true. That is a 0. So in addition to the gates and the symbols, we talked about Boolean algebra. This is the mathematics of digital systems, the mathematics of base 2 systems, and this is called Boolean algebra. And so for Boolean algebra, what there is there's a equation for each of the logic symbols. And this actually does a bad job of the first one, the and symbol. Think of that as multiplication. Now don't say A times B. There's actually a dot in between the A and B, and you would say A dot B, which would be A and B. What you can do once you get used to it, you can omit the dot and it's still A and B because it looks like a product. You can put the A and B in parentheses, that still represents and. You can put the A in parentheses and not the B, that's still an and. Or you can put the B in parentheses and not the A, that's still an and. In other words, any way that you would represent normal multiplication in base 10, that's anding in base 2 when you use Boolean. So any way of showing multiplication is anding. And then here the OR, the way we'll represent OR mathematically is by this symbol here. Now don't say A plus B, that's not what that means. We're using the plus sign to mean OR, so if you read that, you would say A or B, Y equals A or B. And then the way we invert something is we just put this line over it. So this not A represents, if this is A on this side of the gate, then when that A flows through the chip, it comes out as not A. So that represents an inversion. So the Boolean expression for nodding something is just putting the line over it. Remember also I said you can take the variable and put that little prime symbol on it. Sometimes logic is derived, this is all derived from mathematics and mainly philosophy. Logic is a branch of philosophy. And in philosophy, they use that prime symbol a lot. They use Q's and P's for symbols. They represent knots with this prime symbol. So however you want to do that's fine. Just, again, I'll do it both ways. What about the derived functions? Well, there are also Boolean expressions for the derived functions. A NAND is a not and, so here I have A dot B, and to make it a NAND, I just knock the whole thing. Here I have A or B, to make it a NOR, I just knock the whole thing. And then the XOR is just an OR, and the way you represent that in Boolean is just put a circle around the OR symbol, the plus sign. I mentioned that there are some laws. Some of these laws make sense, some you got to think about, but the important thing about these laws is that the left side of the equation, each equation, and the right side of the equation, we don't say that they're equal. This is not an equal sign. This sign means they're logically equivalent. So that's an equivalency sign. So what do I mean by that? Well, if you put the left side in the truth table and you put the right side in the truth table, the outcome in the truth table will be exactly the same for each side of the equation. And I'll actually do an example of that. I don't know if I'll do it today or not, but you'll see how you use a truth table to prove if something is logically equivalent or not. We'll practice that. So you have these laws, and I showed you a bunch of rules, like 10 rules, and I said you don't have to memorize these. I'll give you one homework assignment where you'll use these laws and rules to use these to simplify or reduce logic in a circuit. And so you'll do that for like one homework, but then I'm going to show you a way where you don't have to be familiar with the rules to be able to reduce the circuit. So you don't really have to memorize any of this stuff. Just know that they exist, and then you will use those for one of your homework assignments. This is probably the most important thing in the slide presentation. De Morgan's laws or De Morgan's theorem. And so you don't know why it's important right now, and I will go into details of why it's important later on. But you just have to know how to use De Morgan's theorem on a equation, on the left side of an equation or on the right side of the equation. And I'm not going to go through the theorem per se. I'm just going to give you an easy way to use the theorem. When you use it as a verb, you say we're demorganizing something, what you do is you break the line and change the sign. Break the line and change the sign. So if I gave you this right here, and I say, all right, I want you to demorganize that, what you do is you break that line, so the line is broken over here, and you change the sign. Now I don't have a dot there, but imagine there's a dot in between the A and the B. So if I break the line and each individual variable gets its own not sign at the top, the A has a not, the B has a not, and I change it from a dot to a or, and so I just demorganized that. So we're saying basically the gate symbols, if I go through over here on the left, it represents this gate symbol. And then what I do is I take the input A and I put an inverter on it. I take the input B and I put an inverter on it. Now notice this is not a NOR gate. A NOR gate will have the output inverted, but here I'm inverting the inputs. So when you invert the inputs, you have not a NOR gate, but you have a negative OR gate. So this is a negative OR gate. And so the way you show a negative OR gate is just put the state indicators on the input. So this circuit and this circuit are logically equivalent. And what that means is I can take this circuit or this gate and replace it by this gate, and it doesn't affect the outcome of whatever I'm doing. These are logically equivalent. And then you can do the same thing with this one. If you wanted to, you can demorganize this. So this right here, side of the equation represents this. This is a NOR gate. And if I demorganize it, I break the line. So now the line is broken here and here. And I change the sign from a OR to a AND. And what this says is that this is a NOR gate. And this is not a NAND gate. A NAND gate has the state indicator over here on the output. If I negate the input, I put the state indicator on the input, then what I have is a negative AND gate. And a negative AND gate is not equivalent to a NAND gate. So don't think of it like that. And I'll actually prove that to you with the truth table at some point. Probably not today, but at some point. So that's kind of what we went through, and this is where we left off in the last class. You do want to know how to demorganize, so practice looking at these slides and maybe practice doing some of that. We'll do it when it comes to the point when you guys are programming. I'll show you why this demorganizing is important. And then we ran out of time when we got to this example. So this is kind of where I want to pick up today. So what this is a representation of gates. And this gate circuit, the way it's wired, could perform a certain function, maybe like opening up a garage if certain conditions are true. It's wired to perform a certain function. We don't know what that function is. It doesn't matter, because the point of this exercise is you want to be able to go from the gate or the gate circuit to a Boolean expression. The gate circuit to a Boolean expression. And then ultimately in this class, given a problem in words, I give you a description in words, you should be able to take the words and convert it to gate symbols, and then take the gate symbols and convert it to a PLC program. So that's kind of where we're headed in this. But the first step is to be able to take this gate circuit and to kind of just follow the variables through each gate and see what you have as they flow through each gate. So imagine that the A is flowing into this gate and the B is flowing into this gate. What will this gate do to the A and B? Well, the answer is, of course, if it flows through at this point right here, I'll get this expression, right? I'll get the A, and imagine there's a dot there. I get A dot B, and C just comes right on in here by itself. So I'm going to take this whole expression now and send it into the OR gate, and then take the C and send it into the OR gate. And then what I'll get at that point is this. I'll get the A and the B, and I'll OR this with C. And now I have my Boolean expression. And in theory, well, not in theory, in fact, what you can do now is you can take this Boolean expression, and it's real easy to make a small PLC program by just looking at that Boolean expression. I can do that with switches, relay contacts, or we're going to use something called relay ladder logic. So it's really simple to convert this to a little PLC program. So that's kind of what I want to practice today. So what I have for you is I made this I made up, excuse me, I made up a couple circuits on this handout right here, and I want you to, now remember guys, there's a little box in the upper left-hand corner of your screen. When you mouse over it, turns purple. You can magnify, you can zoom in on this. If you hit that box in the upper left-hand corner, you can zoom in on this to make this a lot bigger. But here are some logic circuits, and what I want you to do is get a pen or a pencil and go through and do exactly what we just did in that exercise. I want you to figure out the Boolean expression for each of these. Go ahead and do the first 5, and I'll switch over to the whiteboard, and we'll work them on the board to make sure we all get the same thing. Do the first 5, and then we'll switch back over to the paper. You can do the last 2, and then we'll switch back to the board, and we'll make sure we work the last 2 on the board. So go ahead and do the first 5 problems here. I'll give you a few minutes to do it, and then we will we'll do it together after that. Make sure you're doing it the right way. It says practice quiz, so I guess at some point maybe you got to take a quiz on this stuff. I don't know. See what you can do with it. Okay, I'll switch back to that in just a second. Anybody get this one? What do you get right here? At this point. What's right there? You guys hear me or you just not talking?
That's going to be AB.
Yeah, it's going to be AB. So right here, you got A dot B, but you don't have to write the dot. We'll just call it AB. That stands for A and B. At that point, you got AB. C comes right on in here, so C is still at this point. And at this point, you're going to take this together, the AB. You're going to OR it with C and set that equal to some letter X, Y, or Z. So there is an expression for that. If I wanted to, in just seconds, I can take this and write it as a little PLC program, as part of a PLC program. So that's the kind of stuff you want to do with the rest of these. So I'll switch back for a couple more minutes to the document, and then you can go ahead and do that first 5. I just want to make sure you're doing it the right way. And then we will proceed with the other 2.
I think you're muted, by the way.
Thank you. You guys see the other example? I erased it. Hopefully you
Yeah,
follow.
I ended up. I assume if you do AC plus BC is also acceptable for the last one. Y is equal to AC plus BC. That's the same thing if you just solve the bracket that you had.
Yeah, let me go back to that. I didn't mean to erase that because I wanted to show the bracket there. So that was what, number 3?
Number 2.
That was number 2. So we had an or. And we had an and. And so at this point, after the and, what I said was, but the audio was off. This is or, so we get A or B. Right? And at this point, this A or B flows through. You cannot just take the C and stick there. What I said was, you got, because this would be anding the C and the B. You want to end this with the whole thing. And then that would be the quantity A or B is ended with C. Now, what was your statement, the person that was just talking?
So I just said is AC plus BC also acceptable, since you're literally just multiplying C and just doing the same thing.
Yeah, so that is logically equivalent. So he's saying, and that's using one of the distributive law from the Boolean rules. He's saying that AC or BC is also acceptable. That's correct. So either way, it's all right. Here you need, here you're taking this. We use 2 gates, but here to implement this, you need an and you need another and then you'd have to take that and or it together. So while both of these are logically equivalent, in the processor, you can take either one of these and put that in the processor for a PLC and run it. And honestly, if this was the only circuit you had in there, it wouldn't matter. But you can imagine if you had a lot of lines of code, then you want the processor to run as fast as possible. So even though the left side and the right side of this is logically equivalent, in theory, this will run a little bit faster because there's less gates. But yeah, you can use either one.
All right, thank you.
So what about this one? We said we take this and end it. So I take A, B, and then when it hits the state indicator, it'll nod it. And I gotta take this and I gotta OR it. I gotta OR it with C. So here's what you can do with this. You can do this if you want. You can say this is OR it with C. Or you don't have to put the parentheses here if you don't want to. Now the one above you had to put the parentheses, but here the bar is like a grouping symbol. So if you want to put this here just for clarity, that's fine, but you don't have to. This bar at the top, the not symbol, is considered the grouping symbol. So that would be written either way for this circuit. And then for number 4, at this point, you're taking A and B. This will not that. And here I can and again, you don't have to put the parentheses. You can just put the C there to and it and set that equal to the output variable. Now, when I have something like this, personally, I'll go ahead and put that in parentheses just for emphasis. That way it's clear that this product is ANDed with the C. But you don't have to. You can actually leave it like that. But make sure you don't accidentally bring your not sign all over your hope. So I would recommend just put that in parentheses, just to be clear. And guys, if you haven't texted me, go ahead and text that number so I can get rid of this. Text your attendance over to me. And then for the last one, number 5.
Is there ever an example while we're doing this where we would have to break the not sign, like where we would have the not over the A plus the not over the B?
You mean where we have to demorganize? Is that what you mean?
Yeah. Do we ever have to do that straight off of a picture, or should we just keep the not sign over both of them?
It depends on what you're doing. Here's where here's where that comes in. Let's say you have this. Um, let's say you have that, and of course this is an AND circuit, and the output is not. So the way, and this is actually the next PowerPoint I'm getting into a little bit, but you'll see it. The way I want to do this in the PLC, if I had this, if I just had this, the way you would represent this in logic using switches is you would take, of course, one switch, call that A, you take another switch, call that B, and then the output over here would be something like maybe a light bulb or whatever it is you're running. So this represents this circuit. The way you do this in the PLC though with software is we're going to replace each of the inputs with normally open contacts. And so the way I would show this in the machine is I take this switch A, put that, replace that with a normally open contact, and put that in a series with B. And then this output that I'm going to control in the PLC, this output represented with this symbol right here, which represents a coil. And again, I'll go over this in the next slide. So the way you think about current flowing from left to right through this circuit to light up the light bulb, you think about power or zeros and ones, however you want to think about it, flowing from left to right through this PLC expression. And each of these contacts would have to be closed in order for the coil to energize, which represents the bulb coming on. Well, the problem is, what if I do this? What if I not this? What if I invert that? So I get A, B, which is what this represents. What if I not that? Well, there's no way to, in the PLC, there's no way to not the output. There's no way to make it negative. You can't not it. So what you got to do is demorganize this. If you demorganize it, you know that A, B, knotted. What I'll do is break the line. I break the line, and I change the sign. So what that's saying is that this is actually logically equivalent to this. And each individual input is not. Well, it turns out that here, if I want to make this, all I got to do is change this to OR logic. Well, that's easy to do. Just put the two contacts in parallel. And in the PLC, you can't, there's no way to not the output. I can't put a not over the output, but I can not an input by just using normally closed contacts. So in the situation where my logic gives me this, I want to implement that in the PLC, there's no way to do it. You just demorganize it, and you got it. Because the left and right side of these two expressions are logically equivalent. So logic, the functionality is the same. Okay, good question. I'm running out of time though, so let's go ahead and do this one. I want you to do the other two. I'd like to get through this other handout. I'll stick around if you have more questions like that, because I got like about 20 minutes before my next class. Let's try to get through this sheet so that we're not behind on Friday. So, let me go to another color. This orange is, okay. So right here, we got A dot B. Then right here, we got a C and a D. At this point, we got A, B. From here, we're gonna OR that with C. And then at this point, we're taking this, and we're gonna AND that with D. So I just put brackets around it like that, and then set it equal to Y. So hopefully you got something close to that. Questions over this? Pretty easy. I mean, it's not rocket science, but you know, if we wanted to, if we have more time, these can get really complicated. We can spend a lot of time doing this stuff, but this is just kind of just to make you think, get your mind wrapped around how you would do this, and then you'll get more practice with this when you do your actual programming in a couple of weeks when you start with the software. Let me go back to the diagram. go ahead and do the last two problems, and then we'll try to get that other sheet out. And then, like I said, if anybody has any questions, feel free. I'll be happy to stick around and do more of this stuff with you. So do number 6 and number 7, and we'll talk about it, and then we'll try to get the other sheet out the way, and then that'll probably be all we have time to do. Oh, I got a PowerPoint I would like to get through, but we'll see how much time we have. I don't know. This hour goes so fast. What you get for this one? Right here. We got C here, D comes through here. Let's flip to D naught. I'm going to take each of those and AND it. So I got A or B. I want to AND this with C and D naught and set that equal to X or Y. That one's not too bad. What about this one though? This is interesting. Now when you look at these logic circuits, the way this works is if you have I can have two wires cross each other like this. I can have two wires cross each other like this if I put a dot there. So this means that those wires are physically connected to each other. And this means they're running over each other, but there's no electrical connection between them. So like right here, I have these wires crossing, but they're actually connected right here. These do not connect. They're connected right here. So there's no connection at that point. These are called nodes. So anytime you have a node, that represents a connection. So here, when you think about the variable flowing through the circuit, A has a path this way and a path down this way. So if it goes this way, at this point, I got A, and this will flip it, it'll knot it. And at this point, this will bring the A right here, unknot it. And this will do the same thing with B. B goes through here, and I've got B knotted, and B also can flow here, and B is unknotted. And so this is going to take each of these terms, and it's going to OR them together. So in this one, I'm going to get A, not B, or A, B, not. I'm going to set that equal to Y. Now, does anybody recognize this right here as, you may or may not, it's no big deal. Anybody recognize this as anything special? I don't know if you can see that far into this yet or not, but anybody recognize that as anything interesting?
Is that an exclusive OR gate?
That is an exclusive OR gate. So I showed you how to, just kind of briefly, how to go from the gate to the PLC logic. I realize we haven't done it yet, but if you can do this right here in the PLC logic that we'll talk about, we won't have time to do the next PowerPoint. We'll do it on Friday. Then you can implement this in the PLC, and we use this as a special type of a circuit that I'll mention later to you. But I'll just say this. Remember this expression right here. So remember this. This is important. The gate representation, not so important, but when we represent this in the PLC, it becomes vitally important to do a certain procedure that we'll talk about. Okay, I got like less than 10 minutes, so anybody have any questions over what I just did before I move to the next slide? Okay, I'm gonna just put this next one on the screen. Just try to go through the whole thing if you can. I wanna try to get this done today. If you have questions, I don't mind sticking around afterward, but I wanna try to get through this so we can get on with the program. So, are you guys able to use the slide bar and slide it up and down, or do I have control over that? Are you able to move the document around on your screen or not?
Yeah, we're able to move it.
Okay, all right. Well then, go ahead and try to do these four, and if you don't understand what it's asking, just ask me and I'll switch over and show you on the camera. So I'll be quiet for a few minutes, and then if nobody has questions, we'll jump on there and we'll solve them real quick. That'll be it for today. I'm a little behind, but that's all right. One more minute, and I want to look at these problems. And again, I might go over a little bit today. I don't know. We'll see what happens. Okay, so here they want us to go the other way. Given an expression, they want you to implement this using logic gates. So right here, you can look real quick and you can see that I have 1, 2, 3 term. A term represents an AND gate, right? So I have 1, 2, I need 3 AND gates for this first one. First one has 2 inputs. The next one has 3 inputs. The other one has 4 inputs. So this is AB, B, C, D, and E, F, G, H. And then I'm going to take and OR these together. So the crosses now are ORs. And so I got to OR the output of each of these together and set that equal to some variable X or Y or Z. And this is the other one. I have now instead of AND gates, I got an OR here. I got an OR here. I got 3 ORs. I got a 2 input OR that has A and B. I got a 3 input OR that has C, D, and E. I got a 4 input OR that has F, G, and H all the way through I. So F all the way through I. I'm going to take them, and then these parentheses represent AND functions, the function of ANDing these together. And so I have that, and then set it equal to some letter X, Y, or Z. So that is really not particularly difficult. We have the De Morganize. So given, and I'll just do the small problem. There's 2 of the same thing repeated. One has 3 variables, the other has 4, but they're all done the same way. So if I have A, wait a minute. Yeah, it looks like I have, my printer didn't print right. It looks like, that's actually one solid line. I don't know how it looks to you, but I have this on my paper. But it's actually one solid line. It should be. It might just be I have a bad copy. But you're going to Morganize this, which means you're going to take this. Remember, there's dots in between there like that. You're going to break the line and change the sign. So this will be A naught or B naught or C naught. And then this side and this side are logically equivalent to each other. And then the one below that is done exactly the same way. There's just 4 variables. Then you have the other one. We're using the OR function, but it's done the same way. You're going to break the line and change the sign. So here we have A or B or C knotted. If I break the line and change the sign, I get A knot, end it with B knot, end it with C knot. De Morganize, you break the line and change the sign. It works every time, and then you got it. So any questions over 3 or 4? Okay, I got like 2 minutes, but I want to do number 5. So if you got another class, go ahead and sign off. But make sure you go back and watch the video, because number 5 is where you use truth tables to see if things are logically equivalent. And so I want to show you how to do that, because number 1 is on your exam, and number 2, you'll have to use that in certain places in the course. So I want to make sure you can do it. And I don't want to rush through it. But I don't want to hold you up from your class either. So sign off and then come back and watch the video if you have to. So the question is this the same as this? Now the same is the left side and right side logically equivalent. And what I mean by that is, well, both sides give you the same value in the truth table columns. Well, what this is right here, what that is this. That's a AND gate that's been knotted, so it's an AND gate. But what this is this. This is a, anytime you invert the inputs, you get the negative of whatever the gate is. So this is a negative AND. So the question is a NAND and a negative AND, are they the same thing? Well, let's figure it out. And the way you build what I want you to do is, when you get to the part of the class where you build your truth tables exactly like this. You got to show me each and every variable. So here's what I'm saying. What you'll do is we have two inputs, A and B. So I'm going to have an A, a B, and I'm going to show all the possible combinations for A and B. That's the first part of my truth table. So what you do is you'll start here with 0. Now, if you have, and I'll give you an equation for this later, but if you have two variables, then you're going to need 4 rows in the truth table. So to make sure you get all the possible combinations, what you want to do is start the first row at 0. And then this one closest to this line, you're going to alternate every other bit for 4 rows. So this is a 0, I change that to a 1, this is a 0, and that's a 1. So I'll alternate every bit, and here I'll alternate every other bit, every 2 bits. So I got 0, 0, 1, 1. And I'll show you how to build up a bigger truth table. But if you do it that way, you have every possible combination of A and B. Also, if you notice, if you're looking at this, you're really counting in binary. This is a binary 0. You know, if you use your 8421 code, then this would be a binary 0. This would be a binary 1. This would be, if I have a 1, that's a 2. In binary, and this is a 3, so you're counting in binary. But there's an easy way to get a bigger truth table, but that's not what I'm going to show you here. So here what I want to do for this part is just cover up the bar and just give me A dot B. If I take A and end it with B, the only time I get a true here is when both inputs are true, and that only happens right here. For every other condition, that column is false. And then to get this whole thing here, I want to take this column and knot that. So I'm going to take this, invert it, invert, not invert. So the value of this is right here. And you knew that because this is the output of a NAND gate. I showed you that in the PowerPoint. So we knew what that outcome was going to be. But the question is, what about this one? Well, what we'll do next is you'll take A, you'll knot A. Well, A is a 0, 0, so here's going to be a 1, 1, and here is a 1, 1, so this is going to be a 0, 0. So there's not A, and then we're going to do the same thing with B. B is a 0, 1, 0, 1, so there's going to be a 1, 0, 1, 0. We invert it, and then we're going to take these two columns and we're going to AND them together to get this. We're going to dot that. So this represents A naught ANDed with B naught, which is the other side of the equation. So if I AND these together, I get a 1. I AND these together, I get a 0. I AND these together, I get a 0. AND these together, I get a 0. And so I want to compare this column to this column. If they are the same, we say, yeah, these two are logically equivalent. They do the same thing. But the fact that they're not the same means that they're two different logic functions. They are not logically equivalent. The point of this example, though, guys, is that when sometimes I have students who go write this, they'll go right to what they think is an answer, you got to show me. See how I broke each of these down into bit. I started with knotting this. I started with anding this. I took the and of A and B, and then I knotted it. You want to be very detailed and show me every step in your truth table. And I'll give you some more of this stuff to practice. I went through this kind of quickly, but hopefully you can kind of see where I'm headed with this. And then when I give you the practice stuff, it'll make it a lot easier. So sorry to go over. I went over like 5 minutes. Anybody have any questions for me before we sign off? Questions, comments, thoughts, concerns? Okay, well, I'm going to prep for my next class. I'll see you guys on Friday. Stay safe, and I will see you soon. Thank you.